Let's now study of an application of stochastic rounding in the context of block floating point format. So here we are looking into MX element rounding, and we'll contrast this with a simple round to nearest even format, rounding format. So I have same example, 0.3, 0.8, and so on, up to a max of 6.96. What I'm doing is I'm calculating the shared scale, then I have this intermediate number, and then I calculate this number using RTNE. So I'll get all these numbers. Then I have an original mean of all these values, right? That's 2.272. I want to achieve that, right? But what happens is that because of this round to nearest even, my total mean over time, once I do all this rounding to all these values, it gets stuck at 2, which is not great, right? You have a negative bias here. So instead of 2.272, you're arriving at 2.0. Okay. Now, in the stochastic rounding, you will be sampling this again and again. And when you run this experiment many times, you will see that over time, as more samples gets accumulated, you will arrive towards the mean 2.272. Whereas in RTNE, your mean never changes because no matter how many times you do, it's a fixed algorithm. Whereas there is a probabilistic approach in the stochastic rounding. So therefore, eventually, with more samples, you will arrive at 2.272 mean. So let's look at this in animation. So as you can see, it starts very high, and then it fluctuates a bit, and then over time, slowly it settles down to 2.272 or close to that. Okay, let me reset and start again. This time it's more clear that over time, it's staying around 2.272, the actual mean. I can change this. So right now there's a negative bias. I can move it to a positive bias. So this has a very positive bias from RTNE. And you cannot fix that using RTNE. But using stochastic rounding, I should be able to fix that. And my original mean is 1.902, and I want to achieve that. So let's start auto in stochastic rounding and take many sample. As you can see, over time, your expected mean 1.902, we are very, very close to 1.902. Right? So that's the advantage of stochastic rounding compared to round to nearest even or any other deterministic rounding scheme. And for element rounding, more than often, stochastic rounding helps. Of course, in hardware, you have to build this, and there is a penalty for that.